Hello and welcome to this Fluid Components International, or FCI, webinar. My name is Katie and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today is Steve Craig. Steve is an International Sales Manager at FCI. Also with us today is Richard Kawikin. Richard is the Regional Sales Manager with FCI. To read more about either of our presenters today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to them to get us started. Gentlemen, go right ahead.
Thanks, Katie, for the introduction. I see we have a large group of attendees. We have an informative workshop today on how to measure direct mass flow in large diameter pipes and ducts. There's an inspiring quote. The most dangerous phrase in the language is, "We've always done it this way." Having always done something a certain way doesn't mean there's not room for improvement. As engineers and technicians, it is important to understand the available technologies in order to make an informed decision regarding which provides the best results for a given application. When multiple options are available, it's best to dig deeper into the total costs of ownership, not just doing things the same as before. I remember 30 or 40 years ago that most technicians and engineers were calculating the orifice plate diameter. Since then, technology has advanced. In today's workshop, we'll be discussing the basics of thermal dispersion technology and fluid dynamics of the air and gas, such as direct mass flow, typical large duct or pipe applications, flow profiles, large versus small pipe diameter. There is a difference between the two as far as flow profiles, and the meter needs to be calibrated to compensate for the difference, and also sizing for the application. We'll also discuss large diameter pipes and ducts, such as multipoint thermal mass flow meters, ISO 10780, which provides guidelines for measuring locations, and installation recommendations, accuracy versus how many measuring points are in the pipe or duct, and also in situ field calibration capabilities to increase the accuracy of the flow meter. And lastly, we'll discuss CEMS, continuous emissions monitoring systems flow measurement with thermal mass flow meters, which includes compliance to government regulations such as US EPA and QAL1, EN 14181, and EN 15267-3. And we'll also discuss other flow meters technologies available. So let's discuss thermal dispersion technology. How is it constructed? We have a flow element, and here you see a picture of the flow element inserted into a pipe, into the media, and at the tip of the flow element, there are two thermal wells. Inside the thermal wells are two RTDs. One of the RTDs is an active RTD. The temperature sensor Platinum 1000 ohm has a heater element installed in the thermal well with the RTD, raising the temperature above the process media temperature. We also have another thermal well. It's called a reference sensor. This reference sensor is another Platinum 1000 ohm, and it's installed in the thermal well, and it's in at the process media temperature. What happens is we have electronics that differentiates that difference in temperature between the reference RTD and the active RTD. As flow increases, the difference in temperature decreases with the flow. So let's talk a little bit more about principle of operation. How does the flow element and sensing element actually work in the gas? We talked about that difference in temperature between the reference RTD and the heated RTD. There's a large difference in temperature because we have a heater element built in with the active RTD. We have an output signal of flow, which is equal to the heat conductivity and the cooling effect. So there's two different ways to cool that active RTD. One is with the velocity of the gas. Increase in velocity, you remove more heat from that active RTD. And also the heat conductivity of the gas itself. If it's a hydrocarbon, it's going to cool at a higher rate than it would with an air. And so we're taking into account that the molecules of the gas are actually cooling that heated sensor. The cooling effect is directly proportional with the mass flow of the gas. Therefore, it's not just the velocity, but it's also the type of gas that's passing by there, that heat conductivity of that gas. The difference in temperature between the heated and unheated sensor represents that cooling effect. And in our transmitter, we account for that because we calibrate in that air and gas at the factory, and we watch that cooling effect of that air or gas passing by that flow element sensor. Therefore, the difference in temperature is proportional with the mass flow rate. And here you can see a depiction of the molecules of the gas passing by the flow element, and you see that gas molecule starting to cool that active RTD, the heated RTD, and as flow increases, it cools it even more. So therefore, we're providing a true mass flow with that flow element, one sensing element in the pipe. And thermal mass flow meters measure the cooling rate of the gas molecules passing by the flow sensor itself. How much the sensors are cooled depends on the actual density of the gas, that heat conductivity, and the actual velocity that gas molecules are passing by. Multiply the internal diameter inside the pipe, and you get a direct mass flow measurement. Now let's take a look at typical applications that have large diameter pipes and ducts. One is flue gas, which is continuous emissions monitoring systems. This can be in a horizontal duct or it can be in the stack itself. And primary, secondary air feeds, the hot and cold ambient air feeds for coal-fired power plants. Combustion air feeds, such as sulfur recovery units, and refineries itself. Flare gas, like on the main header, typically those can be up to 48-inch in diameter. HVAC air ventilation ducts, and main air feeds for typically waste incineration plants, which is becoming a new environmental application. Thermal mass flow meters can have up to 8 sensing points. They can either be on one mast or probe, or they can be separate probes themselves. And these are typically used in large diameter pipes, the ducts, or even stacks such as SEMS. And here we have a depiction of how they would be installed in a stack for a continuous emissions monitoring system. Here we have depicted one flow element and one sensing point, but there's 4 flow elements that are averaged, and the average is 1 420 milliamp output. Let's discuss the differences in the flow profile between large diameter and small diameter applications. In the smaller diameter application, 15-inch or under, typically we have a fully developed flow profile, whereby the velocity at the center line of the pipe is maximum, and near the wall of the pipes, the friction from the walls creates a drag which reduces the velocity inside that pipe. Now remember, we calibrate each flow meter at the factory, so it's important that we calibrate to the correct flow profile. In a larger ductor pipe diameter, it's a flat flow profile, where the Vmax is pretty much standard all the way across. Now this is in ideal conditions, but typically in large ducts or pipes, there's not a whole lot of straight run, so this is only an ideal. And later on in this workshop, we'll discuss how to get around situations where you have very limited straight run. So let's take a look at the difference between a single point and a multi-point flow meter. In most applications, we're used to seeing one flow element in the pipe, which goes back to the transmitter. The transmitter provides a 4 to 20 milliamp mass flow output. But in the larger pipe diameters, we have that flow profile that's supposed to be flat in an ideal condition, but in the real world, typically it's not flat. So we have a disturbed flow profile. To get the best reading inside this large pipe diameter, we actually insert multiple sensing points in there. and we average those sensing points, such as if we have 2 sensing points in that pipe, we take the reading from sensor number 1, add it to sensor 2, and divide by 2, which provides 1 mass flow output. Or if it's up to 4, we take all 4 points, add them up, and divide by 4, which provides for 1 flow output. And it provides better accuracy since you're taking multiple sensing points inside that large diameter. There are different types of multi-point flow element configurations. One is a mast-type, which has multiple flow elements on one probe. It can be up to 8 flow sensing elements on one probe. And again, we're taking the average of that. It can be a probe mast type that extends all the way across the duct, or it can have multiple mast probes, so it can be installed from both sides of the duct or at 4 different quadrants within the duct to be able to provide the mass flow. There's also the single point flow elements, whereby you've got a single point on a flow element and you can have multiple flow elements that go back to a transmitter and provide an average. And again, this can be up to 8 different sensing points on the inside of there. In 15-inch to 40-inch pipe diameters, typically we'll use dual single-point flow elements. In a round duct or pipe, you can see where we locate the sensor in an equal area. So we're averaging the cross-sectional area inside that pipe to be able to get a flow profile. Equal area is established by ISO 10780, and actually the area closest to the wall of that pipe is larger than it is in the center line. That's why these sensors are located closer to the wall of the pipe. And if you look at the duct, a rectangular duct, same thing. We divide that duct with these 2 sensors. We divide that duct into 2 and locate those sensors at the center of that equal area within that rectangular duct. In diameters greater than 40 inches, rule of thumb is to use 4 or more sensing points. And to locate those sensing points, we're still using the equal area application. And when measuring locations greater than 15 inches in a circular pipe or duct, remember we're dividing the cross-sectional into equal areas. And the closer you get to the wall of the pipe, the greater the area. The closer you get to the center line of that pipe, the smaller the area. But let's take a look at this chart. Going across the top, we have a 2-point, 4-point, 6-point, and 8-point. Each of those points, if we use the equal area ISO 10780 guideline on a 2-point system, the first point is located at 14.6% inside from the wall of the pipe. The second point is across the pipe all the way to 85.4% across. And this provides an equal area within that pipe. But in this depiction on the right, we have 8 points. So let's go all the way to the right of this chart where we have 8 points. The first point is located 3.3% from the wall of the pipe or into the pipe. The second point is located at 10.5% and so on and so forth. It's divided into equal areas. And again, remember, the closer you get to that wall of the pipe, the greater the area. Locating the sensors in a rectangular duct, we divide the cross-sectional area into equal areas. Such as a typical single-point flow meter, we locate that sensor at the center line of that duct. For 2 points, we divide that duct into 2 and locate the sensors at the center point of those 2 equal areas. And it's in 3 points, again, we divide that into 3 different areas and locate all 3 flow element sensor points at the center line of those cross-sectional areas. On the left, we have a duct, and again, we're using a 4-point, 2-mast type system, where we have 2 flow elements located on one mast, and there's 2 of those masts which go back to the transmitter to provide an averaged output. Again, we divide up that duct into 4 equal areas, and we're taking the average of each of those areas to provide an accurate flow measurement. In a normal installation with a process connection, such as a flanged, which is recommended, it's normally a 3-inch flanged process connection. It can be threaded, MPT, and here we're depicting a typical mast-type flow element where there is no end support. So it's inserted through a nozzle, and that mast probe can extend all the way to the other side of the inside of that diameter. If you take a look at this, you can see where we take into account when sizing that mast, determining the length of that probe, we take into account the nozzle length, typically a 5-inch or 6-inch nozzle length on there. And then we also take into account how far into that duct or pipe diameter that we're going, and that dictates that probe length or U-length. For mast probe U-lengths longer than 100 inches, it is recommended that we use an end support. We install the mast end support for flows greater than 164 standard feet per second for diameters less than 100 inches. Here we're depicting a mast flow element that's going into the pipe, extends all the way across that pipe to the other side of the wall and past. And we have a support system that we connect to the tip of that pipe, that probe pipe. You can see up in the upper right-hand corner, there is the end of the probe, and there's a threaded NPT. We actually have a cap that fits onto the end of that probe and secures it on the other side of that pipe. So how do you know whether to use a multiple single point or multi-point mast-type flow element? Let's take a look at some of the pros and cons. For multiple single point flow elements, retractable. It can be retracted through a ball valve, and it allows you for ease of cleaning and inspecting the flow element. Variable insertion length. This allows you to be able to do flow profile mapping within that pipe. So you can stick that flow meter in there and take measuring points all the way across the pipe diameter. Take a look at what that flow profile looks like on the inside of there, and it also, you can average those readings to get an averaged output and compare it to what you've got on the flow meter when it's installed. Shorter probe, easier to install. Application-specific flow sensor design. We have different sensors for different applications available. And then cons. Multiple process connections are required. If we look at the mast-type flow element, some of the pros are it can be installed from one side of the pipe, which means if there's obstructions that don't allow you to come in from all sides, you can come in from one side. And it has less process connections. Some of the cons, though, is it's a fixed insertion length. You don't have that variable insertion length, which allows you for flow profile mapping. And mechanical support may be required for larger diameters or high velocity applications. At this time, I'm going to turn it over to Richard, and he's going to begin discussion on installation considerations. It's all yours, Richard.
Thank you very much, Steve, for the excellent introduction into the thermal dispersion technology, the applicability into large diameter pipes and ducts, and the available flow elements. My name is Richard Koeken, and based on our field experience over the many years at customer sites, we have seen that all applications and installations have one thing in common, and that is that they are never the same. It is also never ideal, and therefore we would like to share with you some best practices on actual installations and to provide you with considerations when you are facing these type of installations. First, I would like to focus on this particular installation where you can clearly see that the duct on the right, the customer is intended to have a multipoint flow meter. The thermal mass flow meter is able to measure at multiple points onto one probe, as explained by Steve. In this example, there is no accessibility from left, from right, or from the opposite side of the duct. There are 3 obstructions. How can we achieve a multipoint in this particular installation? If we would need to have 2 points, we can utilize a mast-type flow element, having 2 points on one probe. As shown on this illustration, the probe is inserted from one side of the pipe. And what would we do if we need 4-point measurement? In this case, we would install 2 mast-type flow elements, each having 2 points, and both of those flow elements will be connected to one single remote electronics. The remote electronics will take the average of the 4 points, giving out a 4-point averaged flow measurement. Next to the accessibility around the duct, you also should make sure that there is sufficient clearance available to insert the insertion type device, such as the insertion thermal mass flow meter. As shown on this illustration, by retracting or installing the flow elements, you also should consider that there can be an obstruction in front of the process connection. When you work with the manufacturer to determine the certain flow elements and the length of the flow elements, as these are always customized per application, make sure to consider that obstruction which may be occurring at the opposite side of the process connection. There should be sufficient clearance between the process connection and the obstruction which you have found in the installation. Our recommendation is always to invite the manufacturer on site to have a look together with you on the installation, making sure that all the recommendations are followed. Speaking about accessibility, the flow elements can also be utilized in large diameter stacks to measure flue gas, for example. At stacks, the flow elements typically are installed at great heights to assure that there is sufficient upstream length to get the high accuracy required for emission monitoring. The electronics, however, can be installed remotely up to 1,000 feet or 300 meters away from the flow elements. This has as the benefit that for the purpose of instrument verification or maintenance, the service technician only need to access the electronics first. In the event of a finding, the flow elements can be inspected. The challenge at the flow element side is that the platform at these great heights typically are small. Therefore, it's impossible or very difficult to install a very long mast-type flow element probe. At these short platforms, you would prefer to go with a single point flow element, as Steve already has shown. The single point flow element only needs to be installed at 14.6% of the pipe inner diameter, and therefore can have a short length and easy to remove in case of.
How many measuring points are required or recommended for your application? This basically depends on the cost versus accuracy, and therefore it's not a decision to be made by the manufacturer, but a recommendation together with you. It starts with an evaluation of your application, as the manufacturer can determine the accuracy of the pipe inner diameter versus the number of measuring points. It's important to understand that for process control, the number of points is less important because the repeatability always remains 0.5% of reading for the thermal mass flow meter. In case of redundancies, because of the high safety standards process plants these days have, it is also possible to follow the ISO recommendations in order to have multiple points installed into your single process line. As a rule of thumb, for the optimum accuracy, we have provided the following point selections. Between 15 and 40 inch, 2 points, 40 to 80 inch, 4 points, 80 to 160 inch, 6 points, and above 160 inch, 8 points. Please remember this is a rule of thumb to obtain the highest out-of-the-box accuracy without any in-situ field calibration, and it is not always required to have, for example, 4 points in a 40-inch line. You may be able to control your process using only 1 point. And again, this is depending on the price versus value. On the other side, having 8 points in a 15-inch pipeline will not provide any better accuracy than a 2-point measurement, and therefore it's not required to install a more expensive unit to obtain a higher accuracy, because you won't receive a higher accuracy by simply adding measuring points. Therefore, number 1 is always extremely important to perform a full application evaluation by the manufacturer.
The total measurement uncertainty or accuracy in your application is depending on many factors. We have sorted them in 4 categories to determine the total measurement uncertainty. Number 1 is the base instrument accuracy. This is the accuracy specified typically in the brochure, obtained in a calibration lab in ideal circumstances. Secondly, the determination of the number of measuring points versus the pipe inner diameter. The manufacturer can indicate the additional measurement uncertainty caused by selecting less points in a larger pipe diameter. Thirdly, we check the installation conditions, upstream and downstream lengths. If you have less than 15 D upstream and 70 downstream, typically there is an expectation that there will be an additional measurement error. Lastly, number 4, the in-situ field calibration capabilities can improve the accuracy on site. After the in-situ commissioning by a technician certified by the manufacturer, the accuracy after this in-situ commissioning using the Peter Traverse method is improved. The manufacturer can provide an application evaluation including the determination of the total accuracy for your application. There will be a lot of questions going back and forth to determine the total accuracy for your application. As you can indicate, the repeatability is not affected by the number of points, but the instrument accuracy is the base instrument accuracy specified in the brochure. The out-of-the-box installed accuracy is estimated without any commissioning on site, without the Peter Traverse method. Therefore, this value depends on your upstream and downstream lengths and the number of points versus diameter. Lastly, the manufacturer can provide you with an installed accuracy which may be achievable after commissioning using the Peter Traverse method. Next, we want to explain further in detail the in-situ field calibration. Typically, the requirement is that there are Peter tube test ports available upstream of the flow meter. In this picture, you can see that the flow direction is from up to down. Before the flow meters, before the thermal mass flow meter flow elements, there are 3 Peter tube test ports located. Before we go to explain further in detail the procedure of our Peter Traverse method, we would like to take the opportunity to demonstrate how much dust can be handled by a flow element of thermal mass flow meter. In this installation, as indicated, there are two mast-type flow elements installed downstream of the Peter tube ports. My colleague is opening one of the Peter tube ports in this air feed to start with the Peter Traverse method. While he's opening, there was a certain surprise in the Peter tube and in the installation. There's a lot of dust going through the air feed as demonstrated in this video. Even when he puts his fist onto the Peter tube port, there's a lot of dust coming out, demonstrating the fact that an air feed can contain a lot of dust. The reason that thermal mass flow meters can handle that type of dust is because of the open design. The thermal dispersion technology, as explained by Steve, consists of two thermowells and has an open design. There are no small pores to clog like a Peter tube has. The thermal mass flow meter can handle this amount of dust easily without special consideration or purging. We will further explain the Peter Traverse method in situ calibration in greater detail. On this picture of an application, there are two mast-type flow elements installed with only 5D upstream and 3D downstream lengths, which is much less compared to the 15D upstream and 7D downstream specified by the manufacturer. This is causing a difference between the calibration flow profile regime as shown by Steve, and this difference is causing a measurement error. To lower this measurement error, to improve the performance of the flow meter, a Peter Traverse can be executed. To perform this in situ calibration, it is required that there are Peter tube ports available 300 mm or 12 inches upstream of the flow meter as shown on this illustration. Ideally, there are 5 ports available to insert the Peter tube. During a field commissioning, the field accuracy can be improved by performing this Peter Traverse. On the right, you will see a service technician installing the Peter Traverse. It's installing the Peter tube into the available Peter tube ports at different positions in the pipe. Herewith, we are performing a flow profile research to determine the difference of the actual flow profile in the field versus the calibration flow profile. As shown in the illustrations at the bottom, we are taking many points across the cross-sectional area of the duct or pipe. By doing so, we are able to determine at different loads, different flow rates, the flow profile, and to determine flow profile correction factors. And each point of the flow meter will be corrected based on the findings of the Peter Traverse at different flow rates. These flow profile correction factors will be applied to the instrument to correct for the difference of the flow profile versus the calibration flow profile. One consideration is that for any correction you ever perform, it must be repeatable. That means that the flow profile should not be changing by, for example, a dampener valve upstream of the flow instrument. Please ask for a guidance of the manufacturer with your pipe installation drawings to assure that you have a repeatable flow profile before accommodating for this Peter Traverse method calibration. One of the key applications for the solutions we presented today on large diameter stacks is related to emissions of a plant. Emissions consisting of different components such as CO, SO2, NOx, CO2 will all pollute the environment, and therefore it's important that these are controlled and making sure that these are within the quota
regulated by the local authorities. Typically, the emissions consist of 3 key parameters to be controlled by a system: gas flow measurement of the flue gas composition of the emissions, and dust or opacity, as this has a great impact on the amount of emissions coming from your plant. As these are governed by the local authorities, it is required to install a system called SEMS system, Continuous Emission Monitoring System. This system provides reporting to the local authorities so they can frequently, multiple times a year, audit these reports, making sure that every plant is within their own quota. To monitor emissions, process industry plants install sophisticated SEMS systems, but these can be ineffective if the flow meters selected on which they rely to deliver inaccurate or unreliable data. The following slides will provide some additional guidance to select the proper flue gas flow measurement for your stack. We have categorized 5 main considerations concerning the selection of a flue gas flow measurement. First, you have to make sure that it complies to your local government regulations. Depending on the area where you are located in and the local regulations, these will vary. We will share the 2 key components into these government regulations. Part of the regulations requires regular instrument verification. The instrument verification interval depends on the certificate of the instrument. Some instruments have 4 weeks of maintenance interval, which require a maintenance engineer to verify the instrument every 4 weeks and to report and log this verification. Other instruments have a maintenance interval up to 6 months, which required only twice a year to have a maintenance engineer going to the instrument and verify it every 6 months. This of course has a great impact on the total cost of ownership. One important consideration are also flue gas impurities, as typically there are dust and moisture inside the flue gas. Dust and moisture are no friends of any measurement technology. However, some measurement technologies are affected much greater compared to others. So always keep this in mind when selecting a technology for your flue gas management. You would like to avoid any under or over reporting. While under reporting sounds good, often there are also verification by third parties, by local authorities, which may result into fines, which you want to avoid, as you don't want to have an under reporting. Over reporting is of course also not required, or not what you would like, as this will affect your overall emission monitoring quota. And lastly, we would like to give some additional guidance in selecting the flow measurement technology based on the 4 categories above. As mentioned, one of the key components to select a flue gas flow measurement is to comply with your local government regulations. For example, in the USA, the Environmental Protection Agency, EPA, has provided 2 guidelines showed here, Part 60, Part 75 and the EPI 40. These typically indicate the 24 interval of a zero check and a span drift check for the instrument installed, and it requires automated logging and reporting purposes. A thermal mass flow meter, for example, is compliant to these EPI guidelines with an automated 24-hour drift check, 2 status relays, and it has an automatic logging on the micro SD cards which can be obtained from the instrument. Furthermore, internationally, there are European guidelines, the EN 14181, which supports the automated measuring systems. This guideline supports the EU Directive 2010/75/EU, and it classifies 3 quality assurance level and 1 annual surveillance test, as shown here, which we will address very briefly in this presentation, and maybe we want to have a follow-up webinar to explain this in greater detail. First, quality assurance level Qual 1 requires the instrument certificate, which is obtained by type approval testing by a third party. This type approval testing is performed in the laboratory, but also in the field, as shown on the picture on the right. This is actually in a waste incineration plant measuring the flue gas. This results in a type test report, or also called a Qual 1 certificate, product of conformity. Qual 2 is the calibrate and installation, which requires at installation commissioning and is required to re-perform every 3 to 5 years. Field service technicians which are experienced can be utilized to provide an assurance of correct installation, in-situ field calibration, and next to the commissioning, also your operators can be trained to perform the verification, which is the next quality assurance level, Qual 3. According to the EN 14181, also it is required that an accredited laboratory will come out after the field technician has installed it properly to perform an accredited test in situ. Qual 3 requires the maintenance interval. As already explained, there are different maintenance intervals in the market to monitor and check the drift of the sensors. The Qual 1 certificate specifies the maintenance interval for that technology, for that instrument. Thermal mass flow meter has the longest available maintenance interval of 6 months. It can be performed within less than 30 minutes, and also please pay attention whether it's required to hire the manufacturer on site to perform this check, as obviously the field service technician rates can be expensive for you compared to the operators from your plant to be able to perform the verification themselves. And there is an indication to the operators that the test is being performed by 2 status relays in this example. Lastly, there's also an AST, annual surveillance test, which is required to be performed annually and also to be performed by an accredited laboratory. It's similar like the Qual 2, but at a smaller scale. As mentioned, next to the government regulations and their verification requirements, we are offering a comparison sheet compared to the 3 key flow meter technologies which are US EPA and Qual 1 certified. The 3 technologies which are most commonly used are thermal dispersion, differential pressure, averaging picotubes, and ultrasonic transit time. The only technology which provides a direct mass flow or a normal volume flow measurement is thermal dispersion. The actual volumetric flow measurements such as differential pressure and ultrasonics require pressure and temperature correction. The impact of dust and moisture are negligible for direct mass flow as indicated in this presentation. For differential pressure averaging picotubes, there are the entry ports which can be clogged by dust and requires regular purging of with air, and it's not an assurance that the ports always get cleaned, so retraction of the picotube may be required. The ultrasonics also can be clogged by the dust inside a flue gas measurement. Moisture has an impact on the tubing from the picotube to the transmitters, as condensation may occur resulting in different pressure readings. The ultrasonic flow meters can have the reflections onto the moisture levels with the droplets causing reflections and condensation onto the transducers, which both have an impact on the accuracy, reliability, and with dust getting into the pitot tube, it may even cause no possibility of measurement anymore. Gas composition changes are required to be evaluated for thermal dispersion as these impact the instrument. However, it really depends on the type of gas composition changes, and application-specific recommendations are required. For pitot tubes and ultrasonics, it is negligible impact regarding the gas composition changes. Installation in the same plane, as we have indicated onto the platforms which are available, it is available for thermal dispersion and pitot tubes to be installed in the same plane, but for ultrasonic transit time you would be required to have different platforms at different heights, as it is required to be installed in an angle. Multipoint flow measurement is available for thermal dispersion, and it's very low flow, 0.08 normal meters per second, 0.25 standard feet per second, and a turn down of 100:1 exceeds the other technologies. The operating temperature goes up to 454 degrees Celsius or 1000 degrees Fahrenheit, while the others go to 1472, 800 degrees Celsius and 752 for the ultrasonic flow meters. As there has been plenty of information in this webinar, we would like to conclude with a small summary to indicate the key points which we have discussed. Thermal mass flow meters are direct mass flow meters, not requiring any pressure, temperature or standard density corrections. The number of measuring points is not a fixed value and is determined by the accuracy requirement and installation conditions. Manufacturers offer in-situ field calibration possibilities to improve the performance of the thermal mass flow meter in the field. The measuring locations are per ISO 17080, and the in-situ field calibration can be performed to improve performance with a short installation length and obstructions upstream resulting in flow disturbances. Government compliance maintenance interval, such as 6 months versus 4 weeks, dust, moisture in the gas, temperature, installation, platform obstructions are key considerations for a correct and most suitable flue gas flow measurement selection, for example for your SAMS application. This will conclude our presentation of today, and we want to thank you very much for joining us. We will be answering any open questions you may have during a small Q&A session, or please visit our website to obtain the contact information of the local sales and support office to schedule a follow-up conversation.
All right, gentlemen, thank you both so much for that great presentation. We do have a lot of questions that have come in from our attendees, and we have about 10 minutes for our Q&A session. We are going to answer as many of those questions as we can. So, gentlemen, our first question for today: will each measuring point have its own analog output, or will these be connected to a remote transmitter, which will provide one output?
Hi, Katie. I'll take this one. Yes, each measuring point will be connected to one remote transmitter, and the remote transmitter will average the input from those measuring points and provide an average mass flow measurement through the analog output or Modbus RS-45 or Foundation Field Bus or Profibus communication.
All right, great, Steve. Thank you so much for that answer. All right, let me sift through a couple of these questions here and find our next one. All right, Richard, I think maybe this one would be good for you. This person is asking, does thermal well orientation matter? Parallel to gas flow or versus perpendicular?
Thank you, Katie. That's indeed an excellent question. The orientation of the terminals are indeed important to consider, and generally speaking, these always should be oriented perpendicular to the gas flow direction. Additionally, the thermal mass flow meter manufacturer are typically asking the flow orientation to assure that the same orientation will be used during calibration, and a flow direction arrow will be engraved onto the flow meter to assure correct installation. For example, for installations which have the flow meter installed horizontally, the heated thermal well should be located above the unheated thermal well, to give you an instance. Hopefully this will answer the question correctly.
All right, thank you so much for that answer. So next question here, gentlemen. Steve, I think maybe this one can go back to you. What are the temperature limitations?
Yeah, thanks, Katie. The maximum temperature for the flow element in the process is 850 degrees Fahrenheit, which is 454 degrees centigrade. And it does have a minimum of minus 50 F and minus 45 C. Which covers pretty much every application. The only application that I'm aware of that goes higher than the 850 degrees Fahrenheit or 454 degrees centigrade is on the turbine bypass system. So when the flue gas is going around bypassing the turbine, it's typically up in the 1,000 to 1,200 degrees Fahrenheit range.
All right, great. Thank you so much for that answer. As a reminder to the attendees, we have a ton of questions. We most likely will not be able to get through most of them today. We appreciate your participation, and we will reach out to all of you following today's webinar. So if you do have a question, feel free to ask it, and we'll get back to you. All right, gentlemen, another one here. And Richard, I think this can go back to you. Let's see. This person is asking, you were showing multiple measuring points. How many points can be supplied with one flow measuring system?
Thank you, Katie. Yes, we have shown during the presentation the number of measuring points are depending on the application accuracy requirements. More points do not always necessarily mean additional accuracy. There is an optimum number of points required for the specific pipe size. The additional consideration is the field optimization possibilities. So in the event that there is a field optimization possible, less measuring points can be selected and then corrected in the field on site. Typically, there is, depending on the manufacturer, how many measuring points can be used on one measuring system. For example, fluid components, we have a solution up to 8 measuring points connected to a single remote transmitter. So that's plenty of measuring points for a very, very large diameter.
All right, Richard, thank you so much for that answer. So we do have time for about one more question today. So we're going to do one more, and we appreciate all of your questions. And then we are going to be hitting the top of the hour, so we will start to wrap the webinar up. Again, if you have a question, please ask it. We will reach out to you following the webinar. All right, gentlemen, so the last one for today. Do additional measuring points always result in a higher accuracy? Gentlemen, I can repeat that one. And Richard or Steve, Richard, maybe you can take this one. Do additional measuring points always result in a higher accuracy?
Sorry, Katie, my phone was muted. Excellent question again. So the total application measuring uncertainty, as we have demonstrated during the presentation, is depending on many factors. To answer the question shortly, the answer is no. For example, if you have a 4-inch line size and you have 8 measuring points, that does not mean that you have a higher accuracy compared to 1 point. As explained during the calibrate or during the presentation, there is an optimum number of points available for each line size, and please consult with your manufacturer to determine the optimum number of points for your application. So hopefully that will address the last question of today.
All right, Richard, thank you so much for that last answer. So gentlemen, thank you both so much for a great presentation and for answering a few of the attendees' questions. We have greatly appreciated you being here with us today.
Thank you, Katie.
Thank you very much, Katie, and for all the participants. Thank you for taking the time and joining us into this presentation of today.
All right, and a huge thank you to all of our audience members for being part of this event. Take care, and we will speak with you soon.